research Bioworks is pioneering an approach that enables nitrogen-fixing bacteria to first establish themselves on plant roots before they switch over to fertilizer production mode.
As soon as you engineer a microbe to release ammonia, it's a very energetically expensive process. And that microbe is going to be using all of its energy making that ammonia as a resource for the plant. It can't use that energy for itself. And what that means for the microbe is that it becomes uncompetitive compared to the native microbes that live in the soil that are not making ammonia for plants. And then the engineered microbes start getting outcompeted. So after a couple of days, they're gone because the unengineered native microbes are just healthier. So that's kind of a problem because we have to have engineering to get ammonia out. But as soon as you do that, the product's not competitive. And the way to get around that is to engineer the microbes to first compete with the native microbiome and establish themselves. And after a couple of weeks, once they've established themselves, a genetic switch, which is why we're called Switch Bioworks, turns on. And now they're releasing ammonia. So we kind of get the best of both worlds. Healthy, competitive microbes and engineering to get the ammonia out into the plants. The switch is a programmed piece of DNA that lives in the DNA of the microbe. And it detects changes in the environment that come true after about 6 weeks to trigger this ammonia production. And we're in the product development phase right now, so there are several switches that could be the best product, and we don't yet know which one it is. Okay. So we're working on many switches in parallel, and most of our IP is around the switches themselves. So there's many options. The question is what's best, and then how do you precisely tune it to do what you want at the right time? And we're thinking about this as a platform overall. What else can we do? What do you want a microbe to do? And then what would be the best switch for it that we could put in front of it to have it do that with control? If you have a community or a consortium of strains that each occupy different parts of the root, you can make more fertilizer overall. So our initial product will have at least 3 strains, right? But then we're thinking of going to 4, 5, 6, 7 and see how high we can go. At some point there'll be diminishing returns where the added cost of manufacturing one more strain isn't worth the extra output that it generates. And I want to add one more really important thing here. The diversity of strains that we're using in our product has another big advantage, which is, biologicals are often criticized for their unreliable performance across different soils. Yeah. So what if we could build a community of microbes that is built in a way to be resilient and adaptive to function across different soil types? And let's say we have 5 strains in there. And we want to make this thing work across 2 different soil types. Well, it could be that 3 of those strains do well in one and the other 2 in the other soil, and they kind of help each other out. So it's like an insurance policy as well. Yeah, and in farming, everything is about reliability. Our initial go-to-market is an in-furrow formulation, simply because that's the most modular and fastest route to market. We're keeping a really close eye on seed lubricants. If you think about the Meristem, Revline Hopper Throttle, or the Indigo Clip system, can we apply dry powdered microbes to the seed right before planting? Now, seed coats, as you mentioned, I think would be the holy grail, especially if you're on seed in the bag. So to do that, as you mentioned, the challenges are shelf life. And so, 2 to 3 years is what would be needed. It's really hard to keep a microbe alive on a seed with everything else for 2 to 3 years. So it's however not an unsolvable problem. So we're going after that, but it'll take us longer, and it will require partnerships with some of the big seed manufacturers of the world to co-develop such a product. One of the big things about biologicals is their inherent scalability. If you think about the fertilizer industry, it's making fertilizer. We actually don't make fertilizer. We make the thing that makes the fertilizer. So we have to produce much less. And so instead of 100 pounds, right, it's just ounces of powder. And that's cheaper to produce. We have a techno-economic analysis that estimates the product to cost around $1 for manufacturing per acre. Now, that might be off by a little bit, but it's inherently a scalable solution. So we closed a $17 million seed round last summer. So we're okay for now, which I am very grateful for. It's because it is a very tough market. I think in ag biologicals, because there are so many companies, investors are looking for differentiation. What is different about the product? And so the idea behind not just engineering, but engineering with control and having those genetic switches is really interesting. And furthermore, we really understand the mechanism of action. How do these things work? We understand every single base pair we engineer. We understand the product that we're making, and we understand how it gets to the plant. It's not this kind of I don't want to use the word snake oil, but it's not this kind of hand wavy, here's the silver bullet microbe, you put it in and your crop grows better. But no one really knows how, it makes a healthier microbiome or something like that. No, we understand precisely how our thing works, and that, I think, is important as well. Initially, we're targeting corn in the US. That's the biggest market for nitrogen fertilizer. The principle, however, of switchable ammonia release would apply to any crop and in any region. The question just is, do you need a different host microbe that does well on that plant in that soil? Yes. And do you need a different switch that turns on under the right conditions? And so I'd love to do it all at once. Can't boil the ocean, though. So we're starting with corn in the US. Now, we have a lot of support from the Gates Foundation and King Philanthropies to build our solution for sub-Saharan Africa. And the reason that is exciting to me is that farmers there can afford much less fertilizers. I think it's about 1/7 of what US farmers put. And so if you're able to replace or produce about 40 pounds of nitrogen with a biological product, in the US that'll replace like 25% of the fertilizer, but in Africa, that's a huge impact, potentially doubling the amount of food that people can grow. We were founded in 2022, 3 years ago, and have spent the last 3 years in the product development cycle. We're putting products in the greenhouse and the field starting this year, and then we'll keep doing that every year after that. We're estimating to be commercial not until 2028.
Just stepping back, what do you see as the long-term potential of these kind of microbial fertilizer options? I mean, will they ever be able to completely replace synthetic fertilizers, or is it more just about helping farmers reduce the amount that they're using?
I think, whereas I would love to believe that they can fully replace synthetic fertilizer, I don't think that's possible. I think the cap is at about 50%. Fertilizer replacement at yield parity. And the reason for that is back of the envelope mathematics. You calculate how much sugar is in the soil. And that sugar, the energy that the microbes are using to make ammonia, comes from plant root exudates. And we sort of know how much plants release underground. And then you can kind of estimate, okay, with all the inefficiencies, how much ammonia can we make? And that'll replace about 50% of nitrogen fertilizer. Could we go beyond that? It would probably require engineering the plant to release more sugar or some other innovation that I'm not even thinking about. Now that's the upper end. I think for us to be successful, we don't have to be at 50%. I mean, just replacing 25% of nitrogen fertilizer at yield parity would be game changing.